Hello everyone. In today's class we are going to start with the module number 3. In this module we are going to discuss gate level modeling and data flow modeling. So in the previous chapters we have laid the foundation for the Verilog HDL Verilog design by discussing the different design methodologies, basic lexical conventions and few Verilog constructs. Then we have discussed module and how to declare module, etc. And we have not come across the internals of the module. So in module number 3 we are going to discuss about the internals of the module, that is the design, how we are going to design the internals of the module by using the different types of modeling techniques. So we have, as we know, we have different types of modeling techniques, that is gate level modeling, data flow modeling and behavioral modeling, and one more is the switch level modeling. But out of these four we are going to discuss three, that is gate level, data flow and behavioral. In this module we are going to discuss gate level and data flow modeling. So prerequisites for this module from here onwards is digital electronics subject that you have studied in third semester. So if you know the subject digital electronics thoroughly, and if you are able to design the combinational circuits and sequential circuits, then this programming concepts will be very easy. So you need to know the schematic diagrams of the circuits, truth table, boolean expressions and circuit diagram of the different combinational circuits and sequential circuits to understand the Verilog HDL programs. The first one we are going to discuss with the gate level modeling. So as we have briefly discussed earlier, the gate level modeling, it requires a logic circuit to implement the design. So as the circuit consists of the different logic gates like AND gate, OR gate or any other gate, so this type of modeling is called as gate level modeling. So a circuit can be designed by the use of the logic gates. It consists of some predefined primitives, that is Verilog supports basic logic gates as a predefined primitives. So you are going to use those primitives as it is in your program. So these primitives are instantiated like modules, except that they are predefined in Verilog and do not need a module definition. So as they are predefined, you do not require to need a module definition for that one. So that's why it's very easy to use them in your modules. So all the logic circuits can be designed by using basic gates. So as we know, all the gates are available: AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR gate and XNOR gate. Out of this, the basic gates here, gates are AND gates and OR gates. So these 6 gates can be designed here. So there are two classes of basic gates. The first one is the AND OR gates and the second one is the buff or NOT gates. So in AND OR gates, all the 6 gates we can design except NOT gate. In second one, we can design NOT gate as well as the buffers. The first one is the AND OR gates. So as we know, AND OR gates have one scalar output and multiple scalar input. So as we know, any gate, it produces only one output, whereas it can have two or more than two inputs. That's why we can say that it is a scalar output, one scalar output and multiple scalar inputs. So we are going to see with the two input gates. So the first terminal in the list of gate terminals is an output and the other terminals are input. So remember here, the very important, the first terminal in the list of gate terminals for the gate level programming is always output, then followed by the inputs. So first terminal in the list of gate terminals is an output and the other terminals are going to be inputs. The output of a gate is evaluated as soon as one of the input changes. So it just follows the truth table of that particular gate. That's why the output is going to be changed whenever any one of the input changes. So as per the input combination, its output is going to be evaluated. So the AND OR gates available in Verilog are shown below. So the predefined primitives are nothing but these 6. That is, they are written in a very lowercase letter. That is AND, AND, OR, XOR, XOR, NAND, NAND, NOR, and XNOR, XNOR. So these are the predefined primitives. So the corresponding logic symbol of these gates are shown in the figure. So you are familiar with this. We consider gate with the two inputs. So we can have more than two input gates also, but only one output always. So the output terminal is denoted by out and the input terminal for the two input gates are I1 and I2. So the symbols are shown. So symbols are exactly same as that you have studied it in digital electronics. So symbols never going to change. So these are the gates that are going to be instantiated to build logic circuits in your Verilog programming. So in a gate level programming, we are going to do the logic part using the instantiation. So briefly we have taken some examples in the previous module, but here in this case we are going to deal with few programs that consists of the instantiation part. So examples of the gate instantiation are shown below. So in example, for all instances, out is connected to the output out, and in 1 and in 2, that is input 1 and input 2 are connected to the two inputs I1 and I2 of the gate primitives. So as in our symbol, the terminal names are out, I1, I2. So those names are going to be used. So note that the instance name does not need to be specified for primitives. So it is not compulsory that instance name has to be present, but for sake of simplicity or to understand better which gate actually you are instantiating, it is better to mention the instance name for each and every instantiation part. So this lets the designer instantiate 100 of gates without giving them the name. Without instance name also you can designer can design the instantiation of n number of gates. So more than two inputs can be specified in a gate instantiation. So example, gate instantiation of AND OR gates. So before this, you know how to declare the variables, signals, etc. So after the declaration part, if you are asked to design your program using the gate level modeling, then this type of instantiation is going to be used. So after the module initiation, initiation and declaration part, so this instantiation part follows. And is a primitive, predefined primitive. A1 is the instance name. Out is a terminal name. So recall the symbol of AND gate. AND gate symbol consists of one output and two input, and output is OUT and inputs are IN1 and IN2. So To instantiate the AND gate, so use the AND gate primitive, that is AND, and A1 is the instance name. It is not compulsory. A1 you can skip it, or you can also use it. It is user defined. A1 is the name. It is called as instance name, and it is user defined. Either you can use or you can skip it in this case. So out is the first terminal, which is output terminal, followed by two input terminals, IN1, IN2. Similar to this one, all the other gates are instantiated. So we know the predefined primitives for all the other gates. So NAND, NA1, out, IN1, IN2, separated by commas, termination. OR gate, NOR gate, XNOR gate, XOR gate, XNOR gate, all these are instantiated in a similar fashion for the two input gates. If you have more than two inputs, just include one more input in the list of instantiation. So for example, more than 2 input, 3 input NAND gate is instantiated. NAND, as it is a predefined primitive. Then you can use a instance name. Here long instance name is used, NA1 underscore 3 INP. It is not necessary that you have to use a instance name, or you can use a very short one. Okay, then out, comma IN1, comma IN2, comma IN3. Just see here 3 input NAND gate, how it is instantiated. Just include one more input. So gate instantiation without instance name. So see here, this is without instance name. In previous all the cases we have used the instance name. Just observe the first example for the AND gate and see this example. In this, instance name is missing. This is also allowed. And directly the terminal names, out, comma IN1, comma IN2. So instance name is missing. That is, in previous case it was A1, here it is missing. So this is also a legal gate instantiation. So truth tables for the different gates. So as we have 4 different type of inputs here, that is logic 0, logic 1, unknown, that is X, and high impedance Z. So for all the combinations of these inputs, we should able to write the truth table, and we can simulate them. So for AND gate, when I1 and I2 both are 0, then output is 0. So just recall AND gate. So when AND gate is nothing but it is a multiplication operation, A dot B dot operation or multiplication operation. If any input is 0, the output is 0. If and only if both the inputs are high, the output is high. So based on that, the truth table is written. So for input 0, I1 input 0, irrespective of other input, all the outputs are 0. Similar to that one, if I2 input is 0, irrespective of any input I1, output is 0. So if X is the input, that is unknown is the input, and if your another input is 1 or X or Z, then the output is X, that is unknown. Similar to that one, if the input is Z, that is high impedance, then if you multiply that one with a 1 X or another Z, so output will be unknown only, that is X. So remember here, whenever the input is 0, the output is 0, and whenever all the inputs are high, the output is high. So this is AND gate. Next one is the OR gate. OR gate, if any one of the input is high, the output is high. This is a plus operation, OR operation, not plus. So if any one of the input is high, output is high. If all the inputs are 0, then only the output is 0. So based on that, see the truth table. Third one is NAND gate. So for NAND gate, it is complement of the AND gate. So whatever the output of AND gate is available, just complement it or invert it. So that will be the OR gate, NAND gate output. Similar to that one, NOR gate. NOR gate is complement to the OR gate. So just observe the OR gate truth table and complement the values of OR gate to get the NOR gate truth table. Then the XOR gate. XOR gate, the definition for the XOR gate is, if you have the odd number of ones, then the output is high. So in your, here it is a 2 input XOR gate. So out of this, if you have one input high, another input low, then the output will be high. If both the inputs are 0 or if both the inputs are high, that is if you have a even number of ones in your input, then the output will be low. So you can use Boolean expression also, A XOR B, that is A bar B plus A B bar. So based on that, the output is, truth table is written here. So similar to this one, XNOR gate is the complement of the XOR gate. Just complement each and every output bit, whichever we have the bits. Rest all bits are unknown values only. So we have seen a AND OR gates. The second one is the buff and NOT gates, that is buffer and inverter. So buff is a keyword here and NOT is also a keyword, that is predefined primitive. So buff and NOT, why it is separated? Because in previous case, AND OR gates, they are scalar output, but they have had a vector input, that is multiple scalar inputs. Not vector, they had multiple scalar inputs. But here in this case, this both buff and NOT, they have scalar input, that is one scalar input and one scalar output. That's why they are separated, because they do not have the multiple scalar inputs. They have one scalar input. So one input and one output. So the last terminal in the port list is connected to the input. So first always will be the output terminal and the last always will be the input terminal. So other terminal are connected to the outputs. So it has one input and one output. So the two basic buff NOT gate primitive are provided in Verilog, that is BUF for buffer and NOT for the inverter gate. So see the symbol for the these logic gates. The first one is the buffer and second one is the NOT. Observe carefully what is the difference between these two. That is a bubble. That is for the buffer there is no bubble, whereas for the NOT gate, as you know, it has a bubble. So these gates are instantiated in Verilog as shown in the next slide. So notice that these gates can have multiple outputs but exactly one input, which is the last terminal in the port list. See here, what is the difference here? These can have multiple outputs but they can have only one input. Example for the instantiation, if you take out one as the output terminal and in as the input, then buff is the predefined primitive, b1 is the instance name followed by output and input, that is out1 and in termination. Similarly, not gate, not n1 out1 comma in. So this is how we are going to instantiate buffer and inverter. So similar to this one, we can have a more than one output. So in that case, the example is buff, then followed by the instance name out1 comma out2. Outputs are written first. So if you have two outputs, out1 comma out2 followed by one input, that is in. So without instance name also we can write similar to the AND or gate primitives. Example, not out1 comma in. Just check here for the previous not gate instantiation and this not gate instantiation, that is n1 is the instance which is missing here. This is also a legal gate instantiation. So these are the examples for the gate instantiation of a NOT gate and a buffer. So truth table of this one, as we have it's only one input and one output, so we can have the truth table for buffer and the NOT gate. So buffer, its output is equal to input. Whatever the output, whatever the input is there, so the same will be your output for the bits. So as we have four different types of inputs, that is 0, 1, unknown value x and high impedance value z. So what is the output of those for the buffer? For 0, the output is 0. For input 1, the output is 1. For unknown input, the output is again unknown. But for the high impedance input, the output is unknown. Similar to this one, the NOT gate. NOT gate is just complement of the input. Just invert the bits. So if you have input 0, output will be 1. If your input is 1, output is 0. But if you have an unknown value x, the output is also unknown. If you have a high impedance z, the output is unknown. So for x and z, output is always going to be the unknown value. So these are the truth table of the buffer and NOT gates. So we have a gate with an additional control signal on buffer and NOT gates in Verilog HDL. So see that the symbols for buffer and inverter. So observe the symbol here. It has one more input, that is control, CTRL. CTRL is the one more input which is nothing but a control input. So with this control signal, we have buff if 1 and buff if 0 and not if 1 and not if 0 as the predefined primitives. So there are four different type of primitives here, 2 for the buffer inputs and 2 for the NOT inputs, and the buffer buff if 1, buff if 0 are the predefined primitives for the buffer inputs, and not if 1 and not if 0 are the predefined primitives for the NOT gates. So see here the symbols for a buff if 1, that is a control signal. If 1 is the control input, then only the input is transferred to output, otherwise the output is going to be high impedance. Similar to that one, buff if 0, for that one control input consists of a bubble. Not if 1, the symbol is same, but control input we have a, if the control input is high, then only the NOT gate is enabled, otherwise the output will be high impedance. For not if 0, the control input consists of a bubble. So these gates provides only if the control signal is asserted. That is, if the control signal have some particular input, whichever input that is required for a particular primitive, then only the gates are going to propagate the output. So they propagate Z, that is high impedance output, if their control signal is deasserted. So output is going to be high impedance whenever you do not assert the control signal. So symbol for the buff if and not if already shown in the previous slide. So these are the truth tables for the buffer input 1, buffer input 0 and not input 1, not if 0 and not if 1. So observe there, buffers are going to be give the output same as input, but in this case if the control input is asserted, then only the output will be present, otherwise it will provide a high impedance value. Just check for buff if 1. So for buff if 1, if the control input is 1, then only the output is going to be followed. That's why just check the control input 1. Whenever control input 1 is available, if input is 0, output is 0, input is 1, output is 1. Otherwise, if the input is unknown, output is unknown, and input is high impedance, output is also high impedance. But for control input 0, the output is always high impedance, that is Z. If the control input is unknown, then if your input value is 0, output is low, L. So what is the difference between 0 and L? When you do the simulation, you will better understand. So that will be differentiated in a simulation waveform with the different colors. So when control input is X, the corresponding output for input 0 is L, and for 1 it is H. For X, again it is unknown value. For Z, it is unknown value. Similar to that one, if the control input itself is a high impedance, then if you have input 0, then output L, input 1, output is H, then X, output is X. For Z, output is X. Similar to this one, buffer input 0. So for this one, when the control input is 0, then only the output is going to be present. Otherwise, the output is high impedance. That's why when control input is 0 and input is 0, the output is 0. Input is 1, output is 1. Otherwise, for X and Z, output is X. For the control input 1, for buffer input, buff if 0, the output is always high impedance. Otherwise, for X and Z control inputs, the output is similar to the buff if 1. Similar to this one, the NOT gate. NOT gate, if control input for NOT if 1 is high, then only the output is complemented. Otherwise, the output is high impedance, and other part of the output is just, it is similar to the previous cases, that is complement value. And similar to this one, for NOT if 0, if the control input is 0, then only the output is asserted. Otherwise, if the control input is 1, the output is high impedance. So these gates are used when a signal is to be driven only when the control signal is asserted. So that means in previous case, without control signal, if the input is available, the output is going to be present. But in this case, only if the control signal is provided, then only the output is going to be asserted. Otherwise, output will be high impedance. So such a situation is applicable when multiple drives the signal. So if you have a multiple drivers, then this kind of primitives are useful in those applications. So these drivers are designed to drive the signal on mutually exclusive control signals. So this is the instantiation part of the buff if and not if gates. So just observe, it is similar to the previous one, but here we have one more input, that is control input. So buff if 1 is a primitive, b1 is the instance name, out, in, ctrl, that is control input, that is also included, semicolon. Similar to this one, for buff if 0, that is buff if 0 is the primitive, b0 is the instance name, out, in, control. Just symbol is instantiated here. Similar to that one, not if gates. Not if 1, n1, out, in, control. And not if 0, n0 is the instance name, out, in, control. So please practice all these instantiation part and try to write the programs based on this. That is, the program possible from this discussion is write a Verilog HDL program for all the logic gates. Thank you for watching the video.